Thank you for joining our PPAI panel webinar. So yeah, today we will continue our series of webinar on high resolution model. So yeah, it's my pleasure to introduce Dr. Peter Caldwell to give a presentation today. So Peter is a research scientist at DOE's Lawrenceville Livermore National Laboratory. He is serving a group leader of the climate modeling group. Peter got his PhD from University of Washington in 2007, working with Chris Preston. So I think Peter's research is mainly focused on the cloud and cloud feedback and their role in climate change. Especially, I think is stratocumulus. He is also very actively working on developing high-resolution global and regional climate models. Peter, I think Peter played a very important role in developing DOE's climate model. He was a co-leader for atmospheric and coupled model development for DOE's accelerated climate model for energy, ACME. He's currently leading a team focusing on the numerics of parameterization for DOE's scientific discovery through advanced computing. SciDAC. Yeah, probably Peter can tell more about what is SciDAC. And also the climate model development validation project. So meanwhile, Peter is also atmosphere model working group leader for E3SM. So yeah, today I think Peter is going to talk about his recent work about the simple cloud resolving E3SM model. Yeah, with that, Peter, the floor is yours.
All right. Yeah, so I'm going to tell you about this simple cloud resolving E3SM atmosphere model, or we call it SCREAM. And this is the very, very high resolution atmosphere effort within the larger E3SM climate modeling effort. And E3SM is the US Department of Energy's climate model. Let's see. Oop. Yeah. So I'm going to start out with just telling you about what a global storm resolving model, or GSRM, is, for those that don't know, and then talk about why we might want to build one of these things and why they're the hot topic these days. There's, I think, on the order of maybe a dozen or so modeling centers worldwide that are trying to build them. And then I'm going to focus in particular on kind of the computer science of the model, because that's the thing that makes us unique among these dozen different models. Talk a little bit about our experience with what gets better with the climate and what doesn't. And then kind of step back and talk about what I think are the challenges and outlook for these models before concluding. So, so these GSRMs, they're global atmosphere models, like a typical GCM, but with very, very high resolution. So high enough resolution to explicitly resolve large-scale storms, and in particular, deep convective events, the largest deep convective events. And so what that means is that you typically have a grid spacing that's less than 5 kilometers in the horizontal, which is something like 2 orders of magnitude finer than a typical GCM. In SCREAM, we have 128 vertical layers with the model. Our model top is at 40 kilometers, and so we're not doing a very good job with the stratosphere, which is a problem for if you want to do seasonal to decadal prediction. So you guys will be interested in that. the choice of having a 40-kilometer top was because I love boundary layer clouds, and I wanted to see how well we could do with low clouds as a starting point. But it's really easy. You don't have to change any code at all in order to make the model top higher. So that's something that we intend to do sometime in the future. We're just, where are you going to spend your computational resources? And so we have uh, on this graph here, it shows what our vertical resolution is as a function of how high in the atmosphere you are. And so we have about 50-meter resolution in the boundary layer, 100-meter resolution at the top of the trade inversion, and something like 250-meter resolution in kind of the upper troposphere. We are running with 100-second time step compared to typical GCM uses something like half an hour time step. So very, very short. And this is great for getting kind of extreme events and more realism, basically. And so in terms of the physical motivations for why you would want to increase your resolution by 2 orders of magnitude, the biggest one I already mentioned is that we really want to be able to explicitly resolve deep convection, explicitly resolve storms. And the reason for this is that they've really proven to be the Achilles heel of global atmospheric modeling, in that it becomes clear when you start tinkering with these models at all that changing your deep convective scheme has huge impacts for small changes. And it also is something that people have been focused intently on for the last 50 years, and we still don't have satisfactory deep convective parameterizations. And I actually wonder whether it's possible to be able to get the impacts of deep convection from information that's available on 100-kilometer grid spacing at all. And so this is important. I think something that is being increasingly appreciated is that we've traded one problem for another, and that instead of having to parameterize deep convection, now we have some of our convection is parameterized, some of it's not, and that creates its own problems. So we need clever kind of scale-aware convection schemes that turn off at the right scale. Another reason why we want to have very high resolution in general, so we don't need a 2 order of magnitude scale gap like we do in order to be able to just completely avoid having a deep convection scheme, but just the finer resolution you go, the better you do with topography and orographic precipitation near coastal winds and things like that. So we see a lot of improvements from just having higher resolution. And then another thing that I want to mention in terms of this this graphic on the right is that they're just, in addition to these kind of main issues, there's just so many interactions that occur and are really important in the atmosphere, but they occur on grid scales that are much, much smaller than 100 kilometers by 100 kilometers. And so this example is showing dimethyl sulfide being emitted from the ocean surface. It's really important for cloud condensation nuclei and kind of your cloud morphology. And you can see in this graphic, which is from a 1 kilometer resolution limited area cloud resolving model, that the cold pool left over from convection is acting as a wedge and is shoving the DMS into the free troposphere. So that's really important for the cloud morphology. And this is the kind of thing that you can start to resolve when you have a 3 kilometer grid spacing, and you just are utterly going to fail with a GCM. So lots of reasons to think that it's more accurate. One other point to just make quickly is that we've been using limited area cloud resolving models or storm resolving models for decades now. And so the big new thing here is the global coverage. And that's really critical for weather forecasting on a scale of more than a few days, and for doing climate simulation, because in both cases you have effects in one area of the globe propagate out into the general circulation and affect the rest of the globe. So we really need the global coverage. I think it's an open question of whether we can have a global GCM driving fine resolution just in an area of interest, or whether we actually need the global high resolution everywhere. So that's an area of research that I hope that we'll see a lot more of in the future. Okay, and so that was kind of the science motivation. Hopefully it's compelling enough. But in terms of why there's this huge explosion of these efforts right now, I think the answer is really exascale computers. And so we have these new computers that are just coming on the floor this year, basically, that they're finally fast enough that we can do these kilometer scale simulations and we can run them long enough to start to be able to use them for kind of climate sorts of information. And so in particular, after all the computer science I'm about to talk about, we have been able to run Scream at 0.6 simulated years per wall day on Summit and about 1 simulated year per wall day on Frontier. And so we're not typically going to run in this format because this is using the entirety of the world's fastest supercomputers, but just to say that this is within reach, that you can start to do centennial scale simulations when you can run a simulated year per day. So that's exciting. I think a lot of people are seeing this as kind of the new tool. And the other thing to point out is that these exascale computers, they're potential huge game changers, but they don't help us for all problems. They only help us basically for very, very high resolution problems. And the reason for that is shown on the on this graphic on the right, which on the x-axis is showing the number of nodes of your supercomputer you're using. So you can think of it as what fraction of the machine is getting occupied by trying to run a job of a certain size. In this case, just a typical GCM, so coarse resolution. And then on the y-axis, we have the simulated years per day, or how fast is the simulation running. And so on a typical conventional CPU machine, those are the blue and the black lines for 2 different machines, we see that as you throw more nodes at the problem, you get your simulation faster, which we expect. And it's, when you have twice as many nodes, you get twice as fast a solution, basically. And then the red lines are showing the GPU results. And so on the GPUs, the slope is not as steep, or in other words, as you go to higher and higher node count, you don't get as much advantage. And what's happening here is that GPUs provide a lot of parallelism within each node, so they need a lot of work on each node in order to be effective. And so a conventional GCM doesn't have enough columns to parallelize over, and so we typically are running on this right-hand side of the graph where you just don't really get any benefit from the blue line versus the red line, right? That GPUs don't help you just because there's not enough work to parallelize over. You throw a ton of columns at it, you move onto this right-hand side here, or onto the left-hand side of the plot, and you really get a big bang for your buck, something like a 10 times speed up. So that's another reason why I think there's a push to this very high resolution, because it's the thing that we can do now. I should point out that the Japanese NICAM group have been doing runs of this sort since 2004, so for decades, but they also had the world's fastest supercomputer at the time dedicated solely to their climate problem, which most of us don't have. So to talk even more about computer science for a moment, kind of zooming in on what makes this Scream model unique, it's really how we handled the ability to run on these new exascale machines that have GPUs. And so the critical thing to understand is that because GPUs have all of this on-node parallelism, you want to handle things differently. So the order in which you want to do your loops, the way that you structure your data in memory, so maybe your algorithms, all need to be changed in order to really make them run faster than on a CPU. And so you have to do a ton of recoding. It's a big lift. And so an additional issue there is that different GPU vendors have different programming models you need to use in order to run on their GPUs. And so you could be in the problem where you spend a ton of time getting to run on one machine, and then say your institute buys a machine from a different vendor, and all of the work you just did is for naught. And so adding an extra layer of software abstraction that provides performance portability, so it kind of abstracts out all of these loop order issues and things like that, so that you can have a single code that's able to run on a lot of different kind of programming models, or even different CPU versus GPU architectures, is really popular. And so we're using one of those performance portability techniques, which is to rewrite our entire code in C++ in order to use its templating ability to provide that abstraction. And then we have this externally developed Cocos library, which essentially just provides backends for each specific different GPU or CPU machine that we might want to work on in order to quickly be able to run on different machines. So, and Cocos in particular seemed like a good choice because it's very well supported by the DOE weapons complex, which has very stable funding. Because a critical issue here when you're dealing with kind of this bleeding edge technology is that maybe a tool like Cocos will be supported for 2 years and then it'll disappear and you'll be out of luck. And so we think that this is something that's built to stay. And every time I go to a different modeling center, they're always freaked out and wondering, like, what's the choice that's, which horse should I back that's actually going to be around for a while? So far, Cocos seems like a good bet. Okay, so with that, let me tell you a little bit about what I call the two-pronged plan of how we've built this model. And so what we did is we started out by just taking the existing E3SM conventional GCM, and we extended it to run at very fine resolution. So we had to fix a bunch of problems with memory bottlenecks and things like that. And we just switched out the schemes to Fortran versions of the schemes that we thought we needed in order to run effectively at 3 kilometers. So more high resolution kind of implementations. And we call that Scream version 0. And we started doing science with it in December 2020, so a few years ago. We contributed a 40-day simulation to an international intercomparison of the dozen or so different models that are trying to do this sort of thing. Published an overview paper about it. And so that was really one fork of the plan that allowed us to have atmospheric scientists that were gainfully employed while we did the main thing that we were focusing on, which was to rewrite the entire model in C++, as I just described. We finished that effort towards the end of this last year, so just a couple of months ago. And we were able to do 4 40-day simulations on the Summit supercomputer just in the last month or in the month of December. And so an interesting statistic is we were running at about 4 simulated days per day with the old Fortran code. And then we got on GPUs, got on a bigger machine, and we were able to run something like 40 to 70 simulated years per day in production mode on this new machine. So something like more than a 10x speed up by doing this recoding that allowed us to get on GPUs. So that's huge. We can start to do real science there. Okay, and so one last slide on performance. I'm just showing you the same graphic that I showed before in terms of fraction of the machine versus how fast you're going. I want to point out in particular the blue lines versus the black lines now. And so the black lines are the original Fortran code that we had, so the Scream version 0, and the blue lines are the Scream version 1, so the C++ code, but running on CPUs. So black and blue are both running on CPUs. And so the bottom 2 lines are running on the Summit CPUs, and then the top 2 lines are running on the Perlmutter newer CPUs. And so kind of the punchline here is that we rewrote all the code, spent 4.5 years doing it, and we're getting the same results on CPUs. And kind of the punchline there is that right? Writing your code in C++ is no faster than in Fortran. The thing that we got out of it is that we were able to run on GPUs, so the red lines that are higher. So huge advantage, but not just from writing it in C++. It also turns out, if you compare our GSRM against, in particular, the German GSRM called Icon, which also runs on GPUs, we run about as fast as they do as well. So switching to C++ Cocos doesn't make us intrinsically faster on a particular machine. But the thing that it does do, the thing that we intended it to do, and I think was super successful, is that it allows us to run on these new architectures faster than everybody, or get onto these new architectures more quickly than everybody else. And I think that is going to make us the fastest GSRM. I think it has made us the fastest GSRM. Okay, so let's talk about more of kind of the atmospheric science side of things. I mentioned before the goal here is to not parameterize convection, or at least deep convection. We're using a turbulence and combined cloud scheme called shock, which is allowed or is able to handle skewed PDFs like what you would get with convection. And so it should be able to handle shallow convection, smaller convection in a reasonable way and make our model scale aware, scale insensitive. And it seems to do that between something like 1 and 5 kilometers. We get about the same answers. So that's good. Aerosol is just prescribed in initial implementation. There's a separate project to implement a prognostic aerosol scheme. We're using a non-hydrostatic spectral element version of fluid dynamics, which is just an extension of what E3SM has been using since the beginning. And an interesting wrinkle there is that, so we have spectral elements for doing our dynamics, but it's more efficient to use a finite volume grid for doing your physics parameterizations. So we're actually using a coarser finite volume grid for physics. Speeds up our whole model by a factor of maybe 25%, and gives us very similar answers. So microphysics P3, I think I said, and radiation is RRTMGP, which is kind of the newest blockbuster radiation code that everyone seems to use. So in terms of results, I think I expected the model to be kind of horrible when we first ran it, because we have not tuned the model at all. We just got it working and then just ran a simulation. And there's a lot of things that are really kind of amazingly good. And one of them is the diurnal cycle of precipitation, which is something that conventional GCMs have really struggled with for a long time. But in general, we do quite well. So I'm showing that in terms of just looking over the tropics. Different colors are different times of day for peak precipitation. And the intensity of the color is how strong the diurnal cycle is. And so you see that we have basically the same colors between GPM observations and the screen model pretty much everywhere. I think we have issues with the tropical West Pacific, which show up in terms of having too much intensity. Yeah, that'll show up again elsewhere. But our intensity frequency is also much better in terms of ability to get the strong precipitation. We're able to see the vertical structure of storms in a way that you typically can't. And of course, orography helps a lot as well. So that's an improvement. And precipitation is really critical for impacts. But in terms of climate change, you really need to get the radiation balance right. And so and the key to getting the radiation balance right is getting clouds right. We also do a really good job with clouds. And so showing that here with just a visible satellite image from Himawari on the left-hand side. And then on the right-hand side, we have the same thing simulated by Scream. This is 2 days into a simulation. This is a cold air outbreak off of Siberia. And so you can see it's like pretty much identical. And in general, we're able to get the structure of clouds quite well. One thing that we're not great at, and I think all of these GSRMs are struggling with, is how to handle stratocumulus, boundary layer clouds, which have eddy length scales that are less than a kilometer in general. So we're still just not able to resolve those. So something we're working on. But there are still a ton of deficiencies to the model, and I think it's important to realize this is a very young model. It's only existed for a couple of months in its newest iteration anyways, and so we have our work cut out for us in terms of fixing things. One thing that that I'm really fascinated by is that in this GSRM, and in all of the GSRMs I've looked at, we tend to still have a double ITCZ kind of a shape. So I'm showing in these graphics the precipitation bias averaged over each of the 4 40-day simulations for the 4 seasons that we ran most recently. And so you see these stripes of red, so excessive precipitation, zonally across the Pacific, and that's the hallmark of a double ITCZ. Related to that, the blue, so we have a deficiency. We don't have the Southern Pacific convergence zone quite right either, which I really thought the resolution would fix. So that's interesting. I mentioned before that the West Pacific is problematic in terms of precipitation, also the Indian Ocean. And those, I think, are related to this last point at the bottom here, that we're having a hard time aggregating our popcorn convection, which I think is due to the fact that we have this partially resolved convection. We haven't quite figured out how to deal with that yet. We also have an issue that I think is just related to the way that we've tuned the stable boundary layer, in that we are too warm at nighttime because we have too much mixing down of warm air. We also tend to have these extreme cold snaps that are much colder than we've seen on the planet last couple of hours in polar regions and then go away. So it's a lot of stuff to do still, but generally doing well. I think in general, a lot of stuff is just better when you have such an expensive simulation. Stepping back a little bit, talking about kind of challenges with these kinds of models. So we're able to get to 1 simulated year per day, but our entire annual allocation only gives us about 10 years of simulation. So we're still not able to do these centennial scales. Proof of concept we could if we had the world's fastest supercomputer all to ourselves, but that's unrealistic. So how is that going to change in the future? How are we going to be able to do these longer simulations? I think is a big question. I think the use of these models is also something that we need to be clever about and figure out, in that I think that the most important use of climate science these days is to be able to inform stakeholders about, what are the impacts we're going to see. That requires having PDFs of extremes, which are generally the impacts. And we also need to have significance testing, which, you're just not going to get from 10 years of data. So, so that's a challenge. I think using machine learning to emulate these things is probably the way to go forward. But there's also a lot we can do with short simulations, and that's the subject of this slide, which is basically just to say that I think that these. When I was building this model, I was motivated by the idea that you can calculate your climate sensitivity basically from just doing a pair of fixed SST simulations. So what happens with current climate, then what happens when you just increase the SST by something like 4 Kelvin everywhere. It gives you a pretty good sense of the net feedback. You can do a similar thing to get your effective forcing from greenhouse gases, your aerosol sensitivity. So you can really understand a lot about your model from short simulations. And then in terms of getting at impacts, there's this so-called storyline approach where you run a historical storm. So you do like a weather forecast, and then you do another weather forecast of the same storm, but with the changes you expect to see due to global warming. And so this has become quite popular. It's not a complete answer because it doesn't tell you the changes in the frequency of storms, and it might miss changes in the overturning circulation that aren't captured correctly by your kind of pseudo global warming changes. But yeah, but you can get a lot of useful information. Another huge issue with these models is that, so think about it, you're resolving all of the storms over the whole globe. That's the information you want. You really want to have this fine scale information for looking at, say, impacts or something like that. And as a result, you end up with something like 50 terabytes every month of simulation that you run. And so I made this cute little diagram which shows how many years on the x-axis we would need to run Scream before we had more data than the entire CMIP5 archive. It's something like 3 years of Scream simulation, or the entire CMIP6 archive, which is something like 23 years or so. And so clearly this is not scaling. This is a huge problem. We need to figure out how to really compress the data that we're saving, which is a particular challenge because we can only afford to do like 10 simulated years. There's only a couple modeling centers in the world that can do similar amounts of simulation. And so I think there's going to be a lot of people across the whole world that want to analyze these particular simulations. So there's going to be a lot of use for them, but we need to not save a lot of data. And so a lot of the data that people want to use is probably going to not be saved. It's a real challenge to figure out how to deal with that. Yeah, so I think that brings me to my conclusions. I think these exascale computers are a real game changer. We can do these simulations, so we can do longer simulations, but we need to figure out how to get the allocations we need, how to get the disk space we need, how to make them faster, basically. And I think I am amazed at how much improvement you get in a lot of ways just from explicitly resolving a lot of a lot more scales. But there's things like microphysics are always going to be parameterized. We need to work on that. There's a lot of things that I think are probably low-hanging fruit to really improve these models. So yeah, we have a new set of challenges, which I think is good because the old ones, people have been working on for a long time and they're hard. So hopefully we have easier challenges to overcome right now. So that's it. Thanks.
Yeah, thank you, Peter, for a very nice talk. So I saw Haiyan raise her hands.
Thank you so much, Peter, for this exciting talk, and I have many questions. But first, I think lots of I wonder whether you could tell us a little bit how you initialize Scream.
Yeah. So let's see. Yeah. So we have what to say. That's they're basically we're initializing Scream from reanalysis to get our initial conditions. There's a couple of tools that make that easy to do with CESM and E3SM. So CAPT, there's something called Hiccup that was developed basically by E3SM, and then Betacast. So we've been using Betacast mostly, but kind of we have our hands in all of those. So yeah, I don't know if that sufficiently answers your question, but
a hidden question was whether because I probably missed you probably mentioned somewhere in your talk. Did you run Scream as a AMIP type of experiment or fully coupled?
yeah, so we have only run AMIP, we have only run Scream in AMIP mode. So we're doing basically everything we've done is prescribed SST. We we developed Scream as an atmosphere component of the larger E3SM model, and so that is a coupled model. We have run coupled for a day just to demonstrate that the machinery works. But yeah, that just the way that E3SM is kind of stovepiped the ocean folk, there's the atmosphere folk, this is an atmosphere task. And so we just haven't really gotten it together to do coupled simulation. But yeah, I think it's really exciting. I'm really personally interested in air-sea interaction when you're resolving the ocean eddies, and what is the impact of the clouds above them, I think is an amazing question. So yeah, and I'll also just say that I think there's a real opportunity here, and that we are running our atmosphere, so these exascale machines, I was mentioning they have GPUs on them, but they also have CPUs. We do all of our calculations on the GPUs, and we just leave these state-of-the-art CPUs idle. And so we, on other aspects of E3SM, have been able to run the ocean on the CPUs that we're leaving idle by the atmosphere being on the GPUs. And so I think we can run coupled simulations for about the same speed as we're doing these atmosphere-only simulations now.
Thank you, Peter. One more question before I pass the opportunity to other people. Have you or other people done a parallel experiment with a convection resolving WRF to see the difference or a benefit?
Yeah. So the strict answer is yes, we have. We have a paper in review right now where we've done duration simulations of the 2012 derecho. So particular event where we did the simulations with WRF, we did them with Scream, and I really think that Scream looks a lot better than WRF in that case. So at least in that one case, yes. Maybe you're asking the bigger question of like, well, is there a lot of benefit from doing this global rather than regional simulation? And to my knowledge, that hasn't really been tackled so much. So yeah, I think that's still an open question.
Thank you.
I think next is Victor.
Hi, Peter. Thank you. Very, very nice talk. Can you help me understand how you're not exceeding CFL criteria with a 100-second physics time step? Are you guys doing something implicit in terms of your solver rather than explicit, or are you using adaptive time stepping? Or I'm really puzzled how you're not getting a lot of numeric instability with an 100-second dynamical momentum time step.
Yep. Yeah, so the answer is that we actually, for the dynamics, have an 8-second time step.
Okay.
It's for the land atmosphere coupling and some of the parameterizations, they have a 100-second time step. So
okay,
yeah,
then,
right.
So another in the weeds question, microphysics, single moment, double moment, and have you tested with double moment to see if some of that popcorn convection issue goes away?
Yeah, so we actually can only run double moment. So P3 is a double moment scheme, yeah, which is something I think is unique or at least unusual among these GSRMs. Most of them are single moment.
Okay, and then one thing about your data storage issue, because I completely agree. One thing I think that is going to hopefully continue to revolutionize getting away from NetCDF and Grib2 is the ZAR format, right? And the ability to chunk and get your data into a format where people can really vectorize, depending on if they're looking at ensemble member or the time dimension or whatever that vector be. So if you're not aware of that, I would definitely suggest considering trying to get your output in sort of that format, which will make it a lot more feasible for people to run really, really large, right, cross multi-year, multi-variable statistics on your data. But very, very good talk. Thank you so much for joining us.
Yeah, thanks.
Back, please.
Yeah, I can make this quick. Nice talk. And I just a couple of quick questions. One regarding the Western, your point about the Western Pacific clouds. And so I'm thinking of the maritime continent when you showed earlier that we didn't have a strong agreement with the observational data. What do you suspect is going on there? Is it because of the archipelago and the resolving of the coupled ocean land atmosphere in that region that might not have sufficient, I don't know, initial conditions or something that's missing?
Yeah. I mean, so my first answer is I don't know, but my my intuition is that it has to do with this popcorn convection, the fact that we're just not getting the convection quite right, and in particular the height at which it's detraining is not right, and that seems to be related to it's really a deep tropics phenomenon that as soon as you get off the equator and you start to get some synoptic forcing, goes away. But just if you leave the model to itself, it's not handling convection the right way. So that's my best guess.
Right. And then my other quick question has to do with the, this first comment here on your summer slide that precipitation clouds generally look better. So is there a systematic way in which you're doing that evaluation globally where you can quantify the improvement in precipitation and clouds by these high resolution scheme here versus the standard GCM?
Yeah, the short answer is no. I feel like we're the team that is building the model, or we have been the team that's building the model, and now we have the model as of just like a couple months ago, and now we need to switch to being the team that actually does a reasonable analysis of the model.
Yeah.
So we've done things like create PDFs and of precipitation over certain areas, and they look better and things like that. We have a couple of studies that are just case studies of certain events, like I mentioned the derecho event, where we've kind of more formally looked at like, hey, are things, how are things? But we have not done, and we should do more of a systematic weather forecast style evaluation. So yeah, I'm trying to figure out exactly how to do it. So if you have ideas, I'm all ears.
Okay, great. Thanks.
Yeah, Matt.
Yeah, I just have a quick question. It's obviously, there's no real answer to this, but I'm kind of curious from a practical standpoint, how long do you think at the current kind of development rate you have that this is something that actually becomes usable by the climate community, let alone by the forecasts community? So you need something where you're comfortable enough in tuning it, say, that you could run it over the historical period. How far, even just one ensemble member, let alone doing a large ensemble.
Right.
On the one hand, and then on the other hand, of course, if you were to try to make a forecast out of this on a climate time scale, like you say, you'd need to couple it to the ocean and would need to do some sort of data assimilation that would be usable. So just kind of thinking how far out, I mean, from the point of view of this panel, this is really fascinating and it's a nice glimpse into the future, but I'm curious how far that future is away.
Yeah. I mean, I think one issue that I'm struggling with is that usefulness is a operationalness is a slippery slope, right? So we have a model, it runs stably, it does a lot of things that are better than a typical, at least low resolution model now. And so is it ready for use now?
No.
No. Yeah, I would always.
It's interesting. I mean, from a model development standpoint, yeah, I think that's fascinating. You guys have made a tremendous amount of progress, but yeah, if I wanted to use a model, I wouldn't use a model like this.
Mm-hmm.
Yeah.
Yeah. You wouldn't use it because it hasn't been tested enough, or because even the little bits that I showed are like, oh.
It's at this point, I would say it's not a climate model. Like I said, if I wanted to look at a model like this, I would, from a climate perspective, 100 years is a minimum. And in reality, I'd rather have a historical run.
Mm-hmm.
So that's why I'm trying to get a sense of how far away is it in a usefulness sense.
Gotcha.
Yeah, in that perspective, given this panel, given the kind of things we're interested in this panel.
Yeah. So in terms of like how long will it be before we can do 100-year coupled simulation, I wouldn't hold my breath. I would be surprised if, well, so I would be surprised if this physical model was running 100-year coupled simulations in 10 years from now. But I think that before 10 years from now, we'll be using machine learning to emulate this model in order to efficiently get solutions that look very similar that we can easily run for hundreds, thousands of years.
But wouldn't you need a 100-year run to do that? Because I can tell you, doing machine learning on climate timescales, if I have something less than 100 years, it's just probably not long enough. I mean, how many ENSO events are you going to have in your coupled model that you could train any sort of machine learning on?
Yeah, I guess I was thinking, my feeling is that the atmosphere response timescales is short, weeks. I think that you can train the atmosphere machine learning on a lot less than that, as long as it has the right ocean atmosphere interactions. So I don't know. I'm bullish still.
Yeah.
Yeah, but I think it's a good question of like, I think that this is not a perfect model in terms of being able to do these long simulations. And so I think that there's the question of how clever can we be in finding ways that we can do these short simulations that are useful. And I think there's a lot of them, but in terms of that, like, we want basically a GCM that's just really, really high resolution. I think that's a long ways off. One final thing to say is that so the European Destiny project is aiming to do a 30-year coupled simulation at kind of this 5-kilometer-ish resolution in the next couple of years. So they, I don't know, I'm a little bit dubious that they'll actually manage it, but that's a time scale of maybe the Europeans they think they can get there a lot faster than I do.
I think before we go on to any more questions, I just want to point out to the chairs that it's coming up on 2:50, so we can use the time for questions, or we could go into the panel meeting, whatever you guys want.
Is there anybody who hasn't gotten a chance to ask a question? Because if not, I think we should probably.
And you guys can also just email me. So I think hopefully you have my email, and I'm happy to respond that way too.
Doug, do you have a quick question? You can.
Yeah, I have a question regarding the development of this very high resolution model. The strategy for developing climate model, we basically evaluated some kind of mean climate, TOA radiation, and many other things. But for this very high resolution, we cannot do that. So what is your best strategy to develop this high resolution model? How do you measure this is a success or not?
Yeah, I mean, how to say it? So I guess I would say that you're talking about kind of the parameter tuning step at the end, but before that, you decide what parameterizations you want based on kind of physical understanding of what you think is best. That's the step that we've done. We haven't done any of the like kind of final polishing evaluation at all. I think that that's going to be super challenging on a model that you can't really afford to run. So yeah, we've lucked out. We're actually in energy balance pretty well, within like 0.5 watts per meter squared right now compared to series SIN data for each of the individual time periods that we've been running. So, I think a lot of the issues that we struggled with in terms of trying to tune our model seem to largely go away when you're resolving so many more scales. So the model is just kind of intrinsically better tuned. It has less tuning parameters when you resolve more.
Yeah, thank you. So I think it's a 250. Yeah, thank you again, Peter, for your very nice introduction of this very high resolution of E3SM model. I think this is a really new and exciting avenue for the future. It's the next 5 or 10 years. Yeah, so lots of the interesting stuff we can do, hopefully. So
Even if it's 20, it's
yeah,
like
20.
you've got to do these new things. I mean,
Yeah.
I think this has been a really fascinating talk.
Yeah.
So,
Yeah. Thank you again
okay.
for your talk. So yeah.
Yeah, thank you.